This video covers basics of ionic strength and activity coefficients. The first problem we will solve is to find the ionic strength of 0.2 millimolar magnesium chloride solution. Ionic strength is shown by this equation, where mu equals 1/2 times C1 Z1 squared plus C2 Z2 squared, etc. In this equation, Cn is the concentration of species N. All species that are ionic in the solution should be included in this equation. Zn is the charge of species N in the solution, and the Z value is squared, but the C value is not squared. In our magnesium chloride solution, we have magnesium with a 2+ charge and chloride with a negative charge. Note that for every 1 mole of magnesium chloride, there is 1 mole of magnesium 2+ and 2 moles of chloride. Therefore, we plug in concentration of each species times its charge squared. Note that negative charges contribute the same as positive charges since they are squared. Finally, plugging the concentrations in, we now have mu equals 1/2 times the quantity 0.2 millimolar times 2 squared plus 0.4 millimolar times -1 squared. The solution is 0.6 millimolar. Therefore, 0.2 millimolar magnesium chloride solution has an ionic strength of 0.6 millimolar. The next problem we will do is to find the activity coefficient of various species in various solutions. First, we will find the activity coefficient of sulfate ion in solution that has an ionic strength of 0.01 molar. From table 12.1, with an ionic strength of 0.01 molar, the sulfate ion has an activity coefficient of 0.660. Next, we will find the activity coefficient of sulfate ion in solution with an ionic strength of 0.005 molar. Again, from table 12.1, we find the activity coefficient for sulfate with an ionic strength of 0.005 molar, and we find that the activity coefficient is 0.740. Typically, for the same ion, in a solution with a lower ionic strength, the activity coefficient will be closer to 1. Next, we will find the activity coefficient of H+ in a solution with an ionic strength of 0.05 molar. Again, using table 12.1, we find that that activity coefficient is 0.86. Finally, we will find the activity coefficient of chromium 3+ in solution with an ionic strength of 0.1 molar. In this case, from table 12.1, the activity coefficient is much less than 1, it is 0.18. Finally, if we are to determine the activity of a species in solution, the activity is the concentration multiplied by the activity coefficient. For example, the activity of 0.005 molar sulfate ion in a solution with ionic strength of 0.01 molar is found by multiplying the concentration of sulfate ion times the activity coefficient of sulfate ion. Now we plug into the equation the concentration of sulfate ion, which is 0.005 molar, and we multiply it by the activity coefficient of sulfate ion, which we found earlier as 0.660 in a solution with an ionic strength of 0.01 molar. Therefore, the activity of a sulfate ion that has a concentration of 0.005 molar and is in a solution with an ionic strength of 0.01 molar is 0.00330.